name is Chandrakana, and today I'm going to tell you about functional programming for computer-aided design. So in the past decade or two, 3D printing has become really popular. Today you can use 3D printers for a variety of applications, such as automobiles, space programs such as a Falcon 9, 3D printing various body parts, prostheses, and so on and so forth. What's even more exciting is the fact that today, anybody who can spare a couple of $100s can buy a 3D printer and print anything they want. In fact, I have a couple things that I've printed over the years on the slide, and I even have some in my hand that I've been able to print over the years. So the reason this has become possible is because the hardware cost for 3D printers has gone down. Unfortunately, even though the hardware cost is lower now, there are still some problems in the software side. In particular, the design tools that are used for designing 3D models are often not that great for end users. They're mostly targeted towards expert CAD engineers, and they often lack specifications, as a result of which you can't really compose these tools. Furthermore, a lot of the CAD tools are quite expensive. So how do people actually combat with these challenges today? Most people go to websites like Thingiverse and download models like I have done here. So here's a model for a hex wrench holder. And I have this model in my hand. I can show it to you later. The purpose of this is to store your hex wrenches. And I downloaded this model from the internet. So the problem with this model is that when I tried to put my hex wrenches in it, I saw that they were not parallelly sitting together. So I wanted to make a change. So it turns out that if you try to make a change at this level, and this is actually a polygon mesh, it's actually really hard to make these changes. And the reason it's hard is because mesh has almost no abstraction. If you try to make a modification, it'll violate some invariant, and then you can't actually print anymore. On the other hand, if I had access to something more higher level, such as a CAD program, this modification would have been really simple. All we need to do is maybe tweak or add a new line of code, and that would be it. Another advantage of CAD is that it already satisfies invariants, and it guarantees that none of the invariants are going to be broken. So what is the solution to this problem? The solution is probably some tool that can take a mesh and give you back some higher level code in the form of a CAD program. So today I'm going to tell you about this tool that we have built. We call it Reincarnate because it brings meshes back to life. And we have built this tool, and I'm going to tell you how we have done that. So what did we do with this tool in this particular example? So we took the mesh, we sent it to our tool, and Reincarnate synthesized a program at a higher level of abstraction. And once we had that program, we made a one-line change, which was adding a little rotation, and then we printed the fixed version of this program, and it was successful. And I can show you do different comparisons of the models, and I can have proof here that it actually really was successful. So going back to the solution to this problem, so we want to build a tool that can automatically decompile meshes to give you CAD programs. Now, how do we actually do that? So the key insight that let us build this tool was to view this fabrication pipeline as a compiler, because it is a compiler. And if you do that, you can actually use a lot of techniques from programming languages that we all really enjoy, such as denotational semantics, inductive definitions for compilers, and also we can even prove some properties about the compiler. And the reason we do all of this is so that we can use all these foundations to build useful tools like decompilers. So before I move forward, I would like to tell you a little bit about the 3D printing workflow so that you can understand better which part of the workflow we are targeting. So at a high level, the 3D printing workflow starts with an idea, and it literally ends in an object in the real world. So the first step in the pipeline is to actually design the model. So there are a variety of tools you can use for this. There's OpenSCAD, there's SolidWorks, there's Autodesk, and the point is to just be able to articulate your idea in some form. Once you have done that, what you do is you compile it down to a mesh, and that is exactly what we saw in the beginning. The next step is to use another kind of software called a slicer. A slicer slices a 3D model into 2D layers, very similar to how you can slice your bananas for oatmeal. And the reason you do this is because you want your 3D printer to be able to move in 2D layers to print your design. So this is called G-code. G-code is very similar to assembly that can be interpreted by a 3D printer. And finally, your 3D printer is going to take this G-code and print the part for you. And obviously, this always doesn't go very smoothly, so you might have to inspect and check, and you keep iterating this process until you're happy. Okay, so for the rest of this talk, I'm going to focus on one particular part of this pipeline. In particular, I'm going to tell you about compiling CAD to mesh, and then I'm going to tell you decompiling mesh back to CAD. Okay, so now let's begin. The first thing we're going to do is we're going to try to understand what CAD and mesh actually mean. And then we're going to show how we can write an inductive compiler from CAD to mesh. And finally, we're going to show how we can prove some properties about that compiler. So here's the CAD language that we have developed. And here is a very simple program. It represents a cube of unit dimensions. Here's another one that is a hexagonal prism. You can specify the number of sides, excluding the top and the bottom. And here it has 6 sides. You can do more different kinds of things. So here's an example of applying affine transformations. So affine transformations are linear transformations that preserve parallelism. So here we have scaled that hexagonal prism by a factor of 5. You can do more different things, such as here, I've actually subtracted a little hexagonal prism from a cuboid to get one of the holes of the hex wrench that we saw. So taking a step back, if you look at all these programs, you'll see that this is actually a programming language very similar to what we see in our day-to-day life, right? So here are the different primitives. You have affine transformations, you have binary operations, and so on. Great. So we have seen a couple of CAD programs. What do they actually denote? So now let's understand, what does a CAD program actually mean? A CAD program really denotes a set of points. And it's a special set of points because it's a set of points that are inside the program. So for an empty CAD, it's obviously the set of empty. It's an empty set. For a cube, and if the cube is of unit dimensions, this is actually the interval 0 to 1. So all the points that are in this interval. And if you visualize it, you'll see that it's a 3D cube. Okay, so now let's move on to affine transformations. So for affine transformation, it's very straightforward. The denotation of an affine transformation is applying the linear affine transformation to the denotation of the underlying CAD. And similarly, for binary operations like union, you apply the binary operation to the denotation of C1 and C2. Now, it's actually a little bit more subtle than that, because in practice, you have to maintain certain properties that I mentioned in the beginning. So the invariance that the 3D model is actually valid. And in order to do so, you have to use regular open unions instead of just a union on an ordinary set. And I'm happy to talk about this more later. So now let's move on to another form of representing 3D models. This is called a mesh. So a mesh is really a list of faces. And every face in 3D is a triangle. So if you look at a mesh file, if you download something from Thingiverse, you'll see that it's a list of vertices. And these lists of vertices just tell you the triangle. So the question is, why do we need mesh? We already have CAD. So it turns out that if you actually want to write a compiler that takes a CAD and gives you something like a real object, you need to produce something on which you can do computations. You can't really compute anything on a CAD. It's too abstract. So that's why we need mesh. And furthermore, CAD tools are quite expensive. They're often not interoperable. And meshes have standardized forms. And they're quite popular in online repositories. So that's why meshes are really great. OK, so now that we know what meshes are, what does a mesh denote? A mesh, just like CAD, also denotes a set of points that are inside it. Now, how do you actually know whether a point is inside a mesh? So in order to detect whether a point is inside a mesh, we use a technique from graphics. It's called ray casting. So we basically take a point, we cast a ray from it, and we check the number of faces of the mesh that it intersects. If the number is odd, the point is inside the mesh. Otherwise, it's outside the mesh. So at this point, what we have done is we have looked at 2 different representations for 3D models. A surface representation, which is mesh, and the solid representation, which was CAD. Now, these are 2 very fundamentally different ways of representing 3D models. So what we want now is some way to connect these 2. And this is where our insight from the previous slides comes again, that this entire fabrication pipeline is a compiler. So we should think of these as compilers and build tools as compilers. So that brings us to the next part of this talk, which is how to define an inductive compiler. So the compiler, in this case, is a function that takes a CAD and gives you a mesh. Great. So what does the compiler do for a cube? It just returns the mesh of a cube. And for affine transformations and binary operations, it is recursive, so it will apply the affine transformation to the compiled CAD. And for binary operations, it will also apply the mesh operation of a union, in this case, to the meshes you obtain by compiling C1 and C2. Now note that here, there is also some subtleties. You can't just apply a union operation to the meshes. Remember we talked about regular open sets previously. These also exist in the mesh level. And in the mesh level, in order to determine whether a face is going to be kept or dropped in the final compiled mesh, we need to check normals. And I'm happy to talk about normals later if you're interested in this. Okay, so now let's actually run this compiler that we talked about on a simple example. So here's an example of a CAD program that is just the union of two cubes. So we're going to use evaluation context to run this. So the compiler, as you can probably imagine, is going to first focus on the leftmost child. It'll reduce it to a mesh. And then it'll focus on the rightmost child. And in this case, it's a translated cube. And note that there are some steps that I omitted here. And then at some point, it'll find the mesh for the rightmost child. It will replace the whole with the mesh. And ultimately, it'll get all meshes. And at that point, it'll apply the union on the meshes, and it'll give you the final mesh. So this is how the compiler works, using small steps. Now, if you look at the union operation, it's actually tricky. So often, if you have a complex model, you're going to have a mesh that intersects with another mesh. There will be overlapping faces, which in this case means overlapping triangles, and so on. Now, in order to actually, for the compiler to be actually correct, it has to know how to actually split meshes with respect to one another. So that if there are faces that are partially inside a mesh and outside a mesh, it'll actually break it down into completely inside and completely outside. And after doing that, it'll do one more interesting thing. It'll actually determine what faces of the meshes M1 and M2 is it going to keep in the final mesh. For example, if there's a face that is completely inside another mesh, that face doesn't need to appear in the final mesh at all. So all these things are done using normals that I mentioned earlier. Okay, so far, we have looked at two different languages for 3D modeling. We looked at CAD, and we looked at mesh. And we provided semantics, and we even defined a compiler using inductive definitions. Now, remember I said that mesh and CAD are very, very different. One talks about solids, one talks about surface. Now, if you write a compiler from one to the other, you need to actually guarantee that it preserves the semantics. That brings us to the next part of the talk, which is how do we actually prove that this compiler is correct? So the theorem for the statement of the theorem is actually not, you probably have seen this many times. So what this is saying is that for any CAD program, the denotation of the CAD is the same as the denotation of the mesh you get by compiling it. Okay. So the proof of this goes by structural induction on the syntax of E. And you can look at our paper. We have the entire proof. For this talk, I'm going to focus on one specific lemma that we thought was absolutely beautiful because it has a wonderful combination of geometric reasoning and PL. And this is the lemma which says that it basically proves that the binary operations are correct. So in this case, we're talking about union. And what it means is that if you apply a union to two meshes, the denotation of the mesh you get will be the same as the union of the two meshes. Okay, so let's unwrap this a little bit. So what we need to show here is that if a point belongs to the left-hand side, the point has to belong to the union of the right-hand side. Now, you might be wondering, isn't this just set theory? It is set theory, but remember, we talked about regular opens, and we talked about normals. So what's happening here is that we are applying this to union the surface of two 3D models. And in order to maintain certain invariance, we need to first think about whether the resulting sets are actually regular open. And for that, we need to reason about the normal directions to drop and keep faces as required. So all these different things make this theorem a lot more subtle. And I would really encourage you to check out our paper where we have a detailed description of this. So I would like to give you a little bit of an insight of how the proof goes. So imagine you have a 2D mesh, because 2D is slightly easier to visualize. So you have mesh M1 and mesh M2, and they're intersecting. When you union them, you get this. So now what we want to say is, if a point is in M3, it better be either in M1 or in M2. So we use the same technique of raycasting that we saw previously. So we cast a ray from the point, and we check the number of faces it intersects. And if the number is odd, it's inside, otherwise it's outside. Now, because we have already split the meshes, as I explained previously, what this boils down to showing is if you break this ray down into various subregions, depending on the number of crossings, then for every region, if the region is in M3, it either has to be in M1 or in M2. If it's outside both, it cannot be in the final mesh. So this is the intuition for this proof. The entire proof is in the paper, and I'm happy to talk about this more. Okay, so now we have proved a compiler correct. So what's next? So let's take a step back and think about why we were doing all of this. The reason why we're doing all of this is because we want to make a useful tool, essentially a decompiler, that can give us CAD programs back from meshes. So in order to build a decompiler, we first need to build a compiler. And that's what we have done so far. And we have also provided some guarantees about the compiler so that we can get some guarantees about our decompiler. Now let's move on to this decompiler. So remember that example that I showed before, which was the union of two cubes. And we ran the compiler on it, and we saw that how we got the final mesh out of this. Now synthesis can actually be obtained from this exact pipeline simply by flipping the switches, flipping the arrows. Now, you're wondering, is that really true? It turns out that because we have thought about this entire pipeline as a compiler, and we have written down the small step semantics for the compiler, we can get synthesis almost for free by just flipping the arrows. Now, obviously, there are some challenges that remain. In particular, the first major problem is that when you forward compile a CAD to a mesh, you lose information. Now, what that means is that if you look at that blue lozenge shape, looking at that, you can't actually tell whether you got it from intersecting two cylinders. That is actually what we did. Or maybe you got it by intersecting two spheres, or maybe it's just a primitive. There's no way you can tell. So how do we get this information back? So it turns out that evaluation context can be super useful, and that is how we get this information back. So let's have an example here. So imagine you have the union of two spheres, and you want to synthesize a program for this. If you look at the internal structure of these two spheres, you'll see that part of the spheres are inside one another. So these are actually, like, looking at this, you can't actually know that it's a complete sphere. It's a partial sphere, because part of the sphere is inside another one. Now, when we actually try to synthesize a program for this, we get a union of two spheres. And the beauty of evaluation context is that under the context of the union, you can actually replace these partial-looking spheres by total spheres. And what the union operation will do is it will use the normals that we talked about before to drop the appropriate faces and keep the appropriate faces. And when you compile the CAD program back, you'll get the original mesh that you started with. So the evaluation context gives us actual geometric context for synthesis. The next problem is geometric constraints. Now, obviously, if you want to go back from a set of points in space to something more abstract, you need to solve some geometric constraints. And that's where we introduce three oracles that we have implemented. So the first oracle takes a primitive, like any arbitrary-oriented primitive, and returns a sequence of affine transformations that you can apply to it to get back to that original shape. So the way it does this is it picks a coordinate system for the mesh, and it tries to align it to the world's coordinate system shown in black, and then it applies all the transformations that it had to do in reverse order. The second oracle we have is a subtractive oracle. So this oracle takes a mesh, it finds a bounding primitive that can contain it, and also returns some extra thing that you need to subtract from that bounding primitive to get the original mesh back. Now, obviously, you're thinking that there are so many different ways to actually pick a bounding primitive, and that is right. So what we do is we pick the one that is the tightest fit. And what that means is that it has the smallest difference in the volume with the mesh that we started with. And the last oracle we have is an additive oracle. So this is an oracle that takes a mesh, it breaks it into two, and then it tells you that you should union these two to get the original mesh back. Now, there are infinite ways to break a mesh. So what we have is we have implemented two techniques to do this. The first one is a disjoint split, and here's an example of a disjoint split. So the meshes are completely disjoint. You can synthesize them separately and union them together. Another example is a convex split, which is the example of the spheres that we saw. So what this does is it splits the mesh along the plane where the convexity changes. Now in practice, you can obviously have many more different oracles, but it turns out that these three are actually sufficient to represent any program that we can write in our CAD language. Okay, so the last problem is non-determinism. So it turns out that the entire backward process is actually non-deterministic. So let's run the program on a simple example to see how it goes. So we start with the same mesh that we saw before. And essentially, our synthesis algorithm maintains a work list of meshes, and it picks one to focus on, and then it tries to crunch it down to a CAD and so on. So at every step, it will apply all the oracles. So in this case, the additive oracle will just break it down, will tell you that you should union them. The subtractive oracle will give you a cuboid and a cube that you can subtract. And the primitive detecting oracle will actually just not succeed in this case, because we don't have a primitive that is the separation of two cubes in our language. And in the next step, the primitive detecting oracle actually will be successful, and it will actually give you various affine transform cubes. And finally, from each of these branches, you're going to get a program. And at that point, you can use various ranking functions to pick the right one. In our implementations, we often find that the size of the AST is usually a pretty good estimate. So in this case, you're going to pick the first program because it has one less affine transformation. Great. So now let's talk a little bit about implementation. So we have implemented all of this. So we have our own CAD compiler and a decompiler. And not only does it satisfy 3D, but it also supports 1D and 2D. And you can check it out. We have published it as an artifact. And one thing that is really interesting is that when we were implementing our computational geometry libraries, we saw that a lot of the times we ran into a lot of numerical precision issues. And my co-author, Eval, is going to talk about some of the things that he did in terms of exact arithmetic on Thursday. So we have used our compiler for a variety of CAD programs, and here is a model of ICFP that you can see at the top right. So we wrote it in our language, we compiled it down, and we even synthesized it back. And we have also tried to use our tool on about 20 to 25 programs from Thingiverse, which is a real repository that is one of the most popular repositories for sharing CAD models. So that brings me to the end of my talk. So I showed you how you can use functional programming and programming language foundations in fabrication. And I showed you two applications. One is how to formalize CAD and mesh, and how to use that formalism to build the first ever decompiler that can give you CAD programs back from meshes. Thank you.
All right, thank you very much. So we have plenty of questions, but I have time only for one.
Yeah.
So Zach Slider says, like many STL files are not solid hulls, as they contain unintended gaps between faces.
Mm-hmm.
How do you handle models that are not solid during decompilation?
How do we handle models that are not solid?
Yeah, during
So you mean that have holes in them?
That's right.
Right. So I think if you mean that the model itself as a whole, that is actually fine. As long as it's a valid STL file, if you're talking about STL, we can handle that, right? If the STL file itself as a whole, then it's actually not a valid two-manifold. So in that case, our tool will actually not succeed because it's not a valid model. But if the design itself as a whole, then the oracles that we mentioned will actually be able to handle them.
All right, let's thank Chandra and all the speakers of the session again.